19, right? We can start. Okay, I have this slide from last week, and this is I want to summarize. Um, you have this notion of inverse, yeah. So you see that we can define the inverse mapping if and only if the original mapping is bisected. Otherwise, we cannot define the inverse, right? And the inverse defines very simple. So you use the trick, this condition. G compose F is identity on X, and F composes G is identity on Y. If you want to remember, then you can just put here reminder. Then you have this is identity mapping on set X. That means that Ix is going from X to X with the math Ix applying to X equal X for on small x in capital X. Yeah. So if on every non-empty set there is this identity map. So if you replace x by y, then you have I sub y from y to y, I sub y applying to small y equal y for on y in capital Y. Is a reply, is it consider on any set. No, you have this. Okay, this is an what is this? This is I'll return to the slide, and you already had this mapping fx equals psi of x. If you consider the domain is R and the range is R, then this is not a bisective. You know, if you want to consider the inverse mapping, you have to choose domain and range which are good enough so that you obtain a bisective mapping, right? And this allow you to construct the inverse. Actually, we already knew this inverse. This is denoted by psi or psi to the minus 1. And here I want to give you some more inverses. Here, let me write down on the whiteboard. Here, the moment the this moment here. Good, I share the whiteboard, you know. And introduce some more inverse, right? Actually, if I consider this f from R to R as in fx equal x squared, then it's not injective, no, it's not surjective, because you have f of 1 equal f of minus 1, no. This is not injective, so you cannot take inverse mapping. So therefore you have to generate with the domain, no, and the range. So the range is simple. Okay, the domain, if I take this is R plus, so I remind you that R plus is simply the set from 0 to infinity, you know. And then the domain also, the range also R plus. Then actually you obtain this is already so, yeah. So this is already surjective, yeah. So EMF equal f of R plus equal all of fx x in R plus, right? And you obtain this is this is r plus. So this is x squared, where x running on over this r plus, and clearly this is r plus also. Yeah. So this f is in the surjective, you know. F is surjective. And now if you take x f x1 equal f x2, where x1 x2 in this r plus, what you have follows that x1 square equal x2 square, and x1 x2 both greater or equal 0, because this is an r plus, and so it follows that x1 equal x2. So this means that whenever you have x1 x2 in the domain r plus, and you have f x1 equal f x2, then you obtain x1 equal f2. By definition, f is injective, yeah, and therefore f is bijective. And with this property, now we can find the inverse, the inverse. Yeah? So g equal the inverse of g is to the minus 1 going from r plus to r plus, with the property that okay, f to the minus 1 fx equal x for all x in r plus, because here you have domain and range as the same r plus, and if you like you can take on the other hand side this is also x, you know, for all x in r plus. So what does it mean? This means that f composed with f prime with f to the minus 1, we are sure it has inverse because it is bijective. So I am sure that f to the minus 1 exists. And of course, if you want to find f to the minus 1, you have to use these equalities, you know. This is what I want to write here, just to write in explicitly this form, you know. Identity mapping on the set R plus. Now let's put, if you want to find the formula, so you put y equal fx. So this is x squared. So you obtain f to the minus 1 of y equal x. Yeah? So on the one hand, when you put y equal x squared, you obtain fy equal x. And you want to solve for x, and it is x equal square root of y, because x in r plus. If you solve without any restrictions, then you have to write plus or minus, but now you have a restriction that r x here from the domain f is r plus, so our x here should belong to this here. Therefore, there's only one form, x equals square root of y. So this means you obtain x equals square root of y. So the formula for this f to the minus 1, y equals square root of y, but y is just a letter, a variable. So if you don't like y, you can choose to another letter. No? Y is the letter, and we can change to any letter you like. For example, here I can change to x. So we obtain fx. F to the minus 1 x is simply square root of x. Now this is inverse of f. This is a way you can use to compute the inverse. Now you can solve for here. You can solve x for y, and then you have the formula for y, and then you can change the letter, because this is the letter. You can change any letter you like. You don't like y, and you can change to m and blah blah. So even you can change again to this x here. It's no problem. Good. And you can see some other inverse function. For example, if you check f, here I write here from r to r plus, I write here fx. Maybe you already recognize this function. Then the inverse of f. So you can check easily that this function is surjective and bijective. And the inverse, do you remember the inverse of that function? Can you read it for me? The formula, you can use any letter. Do you read it? Can you read it for me? Yeah, what function should we apply here so that we obtain x? So it should be ln, no? So it should be ln of x. So you have ln x equal to x. Right? Blah blah, so many other arc code, arc side, arc down. So good. This is the warm up. So we will go to the next notion.
Teacher.
And I question.
Should the range of f be r positive minus 0?
Yeah, you are right. You are totally right, because it's never 0. Because it should be minus 0. Good. And this should be minus from 0, so that you do not have 0, no? So you have to have here r plus and minus, okay, minus 0. Good. Because ln of x, you see ln of x, define only for x greater than 0. Yeah, you're right. And sometimes we denote this r plus without 0 is r plus star. This is standard notation, is r plus star is r plus minus 0. Good. This is another example, right? It's you already see that e to the x never 0 here, right? Immediately, if you want to have the surjective property, then you have to make a minus 0 here, and then you can take the inverse. Okay, we are going to the slide, and I will give you another notation. Yeah, we are going to the slide, and we go to the next concept, which is algebraic structures, and we start by the most important structure of the algebra, which is groups. Yeah. But before giving you the notion, the concept of groups, I give the first the definition of binary operation. Here is the definition of binary operation. In high school, in secondary school, you already learned addition. Yeah, you already learned multiplication. And last week we learned about composition. Actually, composition you already knew in high school, but we have a more general notion which can generalize all of such a operation, and this is called a binary operation. So I define as follow. So firstly, we consider a non-empty set G, then a mapping phi going from G times G to G. It maps a couple AB, so element of this Cartesian product maps to phi AB, and this mapping is simply called a binary operation. And for operation, we do not write phi AB, but we write in the following way. Instead of writing phi AB, we write A star B to indicate that this is some assignment that's between A and B. No? But actually, this is assignment going from Cartesian product G times G to G. And for operation, we write phi AB as A star B as defined for x couple, x element of this Cartesian product. And you will see immediately easy example. For example, I will take G to be the set of real numbers R, and I take star as at the addition. We learned long time ago that addition is simply assignment. Every couple of numbers, of real numbers, we excite a new number denoted by A plus B. For example, 1, 2 is excited to 3. 1 plus 2 is 3, yeah? And or 2, 3 excited to 5, for example, yeah? This excitement is unique. Whenever A, B are defined, then A plus B is well defined. This is defined uniquely. Therefore, we obtain a well-defined excitement. And whenever you have a well-defined excitement, then we have mapping. And therefore, actually, addition here is a mapping going from R times R to R. So this is a mapping. So we have the binary operation, because binary operation is simply a mapping going from G times G to G. In this case, G equal R. Yeah. Now we recognize that what we were doing before, the addition, simply a binary operation in this sense. Yeah. Similarly, you have, for example, I can take G equal R, and star simply is multiplication. And you have here is actually this is a mapping going from R times R to R. Is every couple AB maps to A multiply B. Now, for example, 1, 2 maps to 2. Now, 4, 3 maps to 12. Now, this we learned in high school, but at that time we do not know this is really a mapping, because every time when you have A, B are given, then A multiply B is well defined. It is defined uniquely. Then you have a mapping. So this is actually a binary operation. And I want to give you one more binary operations that we learned last week. But I want to give you this notion. So if we denote the set F from the set containing all the mapping from X to X. So as I write simply, the set contains all the mapping F from X to X. This is denoted by home X. Home X simply is a set of all mapping going from X to X. And of course, X should be non-empty, because whenever you have a mapping, then the domain in the range is never empty. Then you can define the composition as what we did before. This composition is simply a mapping going from the Cartesian product home X times home X with the value in home X. So I just take the composition of F and G. So Fg maps to F compose G. Because here you have the same domain, the same range. Every domain is X and range is also X. So you can check the composition. And the composition again has domain X and the range X. So zone way well defined. This means you have a mapping. And whenever you have a mapping from the Cartesian product into itself here, then you have a binary operation in this sense. Good. And look again at this. You see, we have some important property of addition. For example, you have here addition is commutative. So A plus B is the same as B plus A, right? Associative. So if A plus B and then plus C, then I can put brackets anywhere I like. This is called associative property. blah blah. The same thing for multiplication. Here you have commutative property, you have associative property. But let's see the example 3. Actually it's again associative. Yeah, if you compose with more it, and then you can put any brackets anywhere and the results are the same. But if you change the order, then the result is changed. Yeah, this means generally composition is not commutative. So we want to collect such a property in a new setting, in a general case, not only in this concrete case, addition, is multiplication or composition, but we want to define a general case, and you have the following name. So I define, of course, a couple G and star, where G is non-empty set and star is a binary operation. Such a couple is called an algebraic structure. Yeah, because it has operation, it has a set. So algebraic structure means a set and binary operation on that, right? And also now we give the name of the property, the same as before, but now for general G. So therefore we consider the algebraic structure. Then we say this star, this operation is associative if we can put brackets anywhere, and the results is the same. So A star B, and then star C is the same, A star B star C. So we can put brackets anywhere and you obtain the same results of the operations. Similarly, so actually you will see all of the operations that we learned up to now don't have this property, associative property. So either it is addition or multiplication or composition is always associative. But for the next property, so the star is called commutative, even only when we interchange the order of elements, then the results unchanged. So A star B is the same as B star A for all A, B in G. Good. As last examples that we saw, so we saw that addition and multiplication of the real numbers are commutative, but the composition of two mappings is not, generally is not commutative. As a next property that I want to show you here is an element E in the G is called the neutral element of G relative to this operator star, if and only if E star A the same as A star E the same as A for all A in G. So neutral element is has a meaning that it doesn't change the other elements. This means when you start with A, start with this neutral element with A in any order, then it doesn't change A, so you still obtain A. This is why the name is neutral. It does nothing. It doesn't change anything. So neutral element relative to the star, of course. Okay, if I have a look again at this structure, example 1, can you tell me with R with this plus, what is the neutral element for this addition in this set R? It's easy, right? What is neutral element?
Zero.
Zero.
Good, 0. So what is neutral element of this R with the multiplication?
One.
Very good. It's a little bit more difficult. What is neutral element in this set? Home X, the set of all mapping from X to X. You recognize this?
Identity mapping.
Identity map.
Very good. Yeah, so you already gave me example here, right? So example 1 is as we already had. So the R, which is addition. So R is associative, commutative, and the number 0 is a neutral element. Clear? R with multiplications also associative, commutative, and number 1 is neutral element. And this home X with is a composition. Home X is associative but not commutative. So this we have to pay attention a little bit. Generally, it's not a commutative because when you change the order of F and G's, and generally they are different. F composite generally is different from G compose F. And the identity mapping IX is neutral element. This is why I already review you at the beginning the inverse mapping. So later on we will return to that kind of inverse. Okay. Normally there are two common ways to. Any question? Remarks or comment? No. So you have two common way to represent the operation, the binary operation. Here I write here. It may be written as addition. Yeah, as previously you see addition in R in and there will be more addition in other set of subject of object we will learn later. But if star is written as addition, then the neutral element we will denote it by O sub G. You have to write this 0 a little bit bigger, because to indicate the neutral element related to the addition, and to distinguish with the number 0, you have to write a little bit bigger. When we already understand what G is, then we just write the 0, with our sub-index here, and call the non-element. So non-element is simply the neutral element related to the binary operation, which is written as addition, right? Another way is sometimes star is written as multiplication. It's not really multiplication of numbers. It can be multiplication of other objects. For example, here, this composition can be considered as multiplication of mappings. We do not say multiplication, but we can read as we can consider is written as multiplication, because it's that multiplication with bigger sign. Then in that case, when star is written as multiplication somehow, then the neutral element will be denoted by 1 sub G, or 1 when G is clearly understood, and we call it the identity element, right? So you can write, there are many names, but every name contains identity. So you can call multiplicative identity, or identity multiplication, simply identity. Here again, here none element is called simply none, if you like. Good. So let me prove something. If you have an algebraic structure G star, so G is non-empty set and star is a binary operator operations on this G. Then if there is a neutral element is, and this neutral element is unique. So let's prove this. It seems very nice now. Actually, this means that if neutral element exists, actually related to star, of course, then it is unique. Sometimes there may occur that there is no element, but if element exists, then it's always unique. So let me return to whiteboard, right, and show you how to prove this. Here, So we can delete that part. So we have here G, an algebraic structure, and E. So there exists E, which is neutral element, related to star, of course. Then we prove that this is unique, It follows that E is unique. This means that we will prove this. This means that let E and also E prime be two neutral elements. Of course, related to star, we will prove that E and E prime should be the same, because then it means that E is unique. So let's take E star with E prime. Now pay attention that E prime is neutral element, so this should be E, because neutral element doesn't affect any element, any other. So when E prime is element, then E star E prime should be E. But on the other hand side, E also neutral element, therefore this should be E prime. Because I remind you, is neutral element if and only if A star E the same as E star A, the same as A for all A in G. So in here we use the fact that E prime is neutral element, so E here plays a role as A here, so, and then we take advantage that E is also neutral, then E prime here plays a role as A here, right? So we will change E prime equal E, so this means that it is unique, and we are done. Good. This is very simple proof, and this means that neutral element, if exists, is clearly unique. And the proof I already wrote in the slide, but I already write here, so you don't have to read the slide. So I return the slide, and here I write the proof here, but it's redundant now because you already saw in the whiteboard. I'm going to the structure group, which is very important structure. This is a fundamental structure of algebra. So here's the definition of the group. You have an algebraic V and star, or as above, G is a non-empty set and star is a binary operation on G. Now this algebraic structure is called a group if and only if these are three property holds true, right? So the first thing is the star is associative, and second is there exists neutral element E in G related to star, and we know that this should be unique, because if it exists, the neutral element will be unique, And the third means that for all A in G, there exists A prime also in G, such that A star with A prime equal A prime star A and equal this E, this neutral element. So we call this is a group if and only if these three properties are satisfied. So pay attention here. You see that we require only star is associative, because this is the most common property of operations. As you see in previous example, we have almost all of the operation up to now we knew this always has this property about associative property, you know. But sometimes if we are lucky, the star may be also commutative. For example, if star is addition, then it is not only associative but also commutative. In that case, we will give some more name to a group. This is what I want to give you here. So if the star is commutative, then I call this G star. Of course, suppose a G star is already a group, right? And now in addition to all the group property, if the star is commutative, then we call the group is commutative group or abelian group. This is the name is the same as commutative, but this is come from famous Norwegian mathematician. This is Abel or Aben in Norwegian, you know. This is very famous. There is a prize named Aben Prize, you know, for famous mathematician. Okay, this is the same as commutative. You can say commutative group or abelian group. Another name here is for the last property in group, we mean that actually for all A in G there exists A prime such that A star A prime equal A prime star A equal E, which is element neutral element, and this A prime is also unique. No, for A the element A prime such that A star A prime equal A prime star A equal E is unique, and this is called opposition of A. Actually, the proof that A prime is unique is almost the same as the proof that a neutral element is unique. You can imitate that proof to do the proof yourself, you know. But now I want to pay attention to the name of this A prime. As I said before, there are two common ways to write or to represent the operation star, binary operation star. So the first way is star can be written, may be written as addition, or the second is maybe written as multiplication. Correspondingly, this A prime will have the corresponding name, right? So here, of course, we still suppose that G in stars is a group, no? Then it is called additive group if star is written as addition. So I write it's equal, but you should think of star written as addition. And then in this case, this A prime is written as minus A, so negative of A. We call this negative of A because it has minus here, you know. Actually, when you see when replace star by plus, then actually A plus minus A is 0, and 0 is the notation for the neutral element related to the addition, right? And what happened when star is written as multiplication? Then if star is written as multiplication, then we call G star as multiplicative group. No? And this opposition A prime is denoted by A to the minus 1. So the inverse of A. No? So this would be more convenient to you A prime. This is more convenient to you minus A if the operator is written as addition, or we use A to the minus 1 if addition if operation is written as multiplication is more convenient. Okay, now let's take example here. So R with plus with the addition. Okay, let's look at addition is clearly a commutative and associative. It is not only associative but also commutative, you know. And as you said before, the neutral element is 0, no? The number 0. And every A in R, so the A prime will be exactly minus A. In this case, you see the notation is perfectly, you know. Okay, so I write in the whiteboard so that you can see once again this is property. I write in whiteboard. Here you have this R and addition, yeah. So you have addition is actually associative. I write shortly. Commutative and neutral element. In this case we call non-element, yeah. Is 0 clearly, because A plus 0 equal A for A in R, right? What is more? So for all A in R, so there exists opposition, but in this case we call negative. So actually this is simply minus A. Actually minus A is of course also in R, and if you take A plus A prime, it's A minus A, you know, which is 0. So in this case you don't have to change the order because the addition here is already commutative, you know. So you just have to write in one order. This is enough because it's already commutative. So therefore you obtain this is a billion or commutative group. Good. And now we can return to the slide, and I want to ask you a question here. We return to the slide and ask some question. Here we have this R with addition is a billion additive group. The group is called additive because the operation here, binary operation here, is written as addition. The name additive group just means that the operation is written as addition. Good. And what is more, I want to ask you, what about this R with multiplication? Is that a group or not? If it is a group, why? And it is not, if it is not a group, tell me the reason why.
It's a group.
It's a group.
No,
Oh, it's not a group.
it's not a group. No.
Oh,
So
wait.
pay attention to the last property, you know. So the inverse of A, for the multiplication we call Abraham's inverse, and is wrong when you take A equal 0, then there is no inverse of A. Can you see this? No. I think that we have 10 minutes break now, so well, you have 10 minutes break and we resume after 10 minutes. Okay, have short break and see you later after 10 minutes. Okay, we continue with this question. What about R and multiplication? So I will explain shortly here. Okay, let me use this whiteboard. Okay, here this is whiteboard here. So we had now we had R with multiplication. Yeah, of course. Again, you have this multiplication associative. Why? Right? And not only associative but also commutative and a neutral element. In this case, we call identity multiplication or multiplicative identity. So actually, neutral in this case, neutral element is called identity. The full name is multiplicative identity or identity multiplication, whatever what it contains identity. You know? Identity element is one clearly. But now let go to the last property of a group. So we see that if I take a equals 0, then let me choose a prime in R such that a prime multiply 0 equal 1, but it's never happened because a prime multiply 0 is always 0. It's never equal 1, right? This means that there is no a prime such that a prime multiply 0 equal 1, right? So what does it mean? It means that when a equals 0, there is no inverse away, no? So this means that you take 1 over 0, then it is not defined. And therefore, we obtain that this not a group, right? Là it's not a group. What we should do if we want to obtain a group, so we have to change it R now. So it's very simple. You know how to do this now. We'll eliminate this 0. No? So I take
star.
Yeah, R star, of course. So I take R, subtract 0, and then this multiplication. Then we immediately this situation doesn't occur anymore, right? Because every member of this set already is not 0. So whenever a in this R subtracts 0, then a is not 0. And therefore there exists a prime, which is simply 1 over a. When you multiply a prime multiply a, you obtain 1, right? Okay, this is the next example that I want to give you here. Okay, we'll return to the slide. Good. This R and multiplication is not a group, but if you subtract this 0, and again we consider multiplication, then it has everything, every property of a group, and moreover this is a billion group, so commutative group. Multiplicative group, the name multiplicative here just means that this binary operation here is written in the form of multiplication. The next time, okay, I exercise homework. So the put again we consider non-empty set X. if you consider home X, look at, okay, let's return to the here, home X. Home X is a set of all mappings going from X to X. And you consider the composition, then actually it has neutral element, which is identity mapping, clearly. But if you consider general mapping, then it may not have inverses. Why? Because if you want some mapping to have some inverse, then the mapping has to be bisective, right? That's what, this is what I want to remind you at the beginning. Here's the inverse mapping. So the mapping wants to have some inverse, and it should be bisective mapping. Therefore, I consider the following examples, and you can check at home. So now I consider nx defined this way is a set of all bisective mapping from X to X. It's not only a mapping, it is bisective mapping. Yeah. Then actually bisective mapping always has an inverse, and this we have the property 3 of the group satisfied. Yeah. Then you can prove easily that nx, which is composition, is group. But actually remember, the composition generally is not commutative. Yeah. So we obtain although this is group, but it's not commutative group. No. And the neutral element is identity map. Okay, you can do as homework. I hope that you can do this because it's not so difficult now. And are there any questions? No? Okay, then I have a question here. The question is why we need group? No? Why do we need group? Is it just for fun? When we learn something, we ask what for, right? Oh, okay, I said here again the whiteboard. No, I delete this on the. Okay, the question very simple. Why group? Oh, I have to write in a nice way. You know what happened with my handwriting? Why group? Why we need to learn group? Why do we learn group? Is that for fun? um, Actually, um, the important thing, the important important feature of group lying in the fact that we have to show equation. You know? Actually, you in high school you show this equation, and it has solution if you have if you can change. So actually, it's equal to x equal b minus a. You can obtain that in the group Z plus, for example. You know? If you consider n plus, then you cannot show that. Why we can show this equation? Because this Z and plus has structure of a group. Generally, if you have G star, which is a group, then for A, B in G, which is given, then you can solve. We can find x from this equation A star x equal B. Let me tell you how to solve this. This is not only in Z, not only in R with plus or with multiplication, but it's true for any other object which has properties of the group. This means that we can apply our experience and our techniques that we had before to the new object. This is interesting. This is the purpose of generalization. Generalization is very nice because we can it help us to apply our old technique, our old experience to a new subject, to a new object, provided that new subject or object has a property of the same thing that we had before. Then we can apply our old experience to the new object. So let's solve this. Okay, we know this group. So for A in G, we know this is group. So there is this A prime also in G with the property that A prime star A equal E, which is neutral element. Yeah. So therefore I can take the star with A prime. But now you see that in a group we have the fact that the star is associative. So you can put brackets here. And here A star A you obtain E, but E is neutral element. E star X is again X. So you see, I have to mu, yeah, and to mu on. And then if you have any question, use it. Okay, you good. Then at the end you obtain, you can compute X. Yeah, the same way as what you did with addition here, right? So this minus A is inverse, this is the opposite of A. So minus A is actually A prime. When the operation is written as addition, we denote A prime by minus A. You see here, so I should write this way, it's better. Just try in the right way, so should be minus A. Okay, minus A plus B. No, we are lucky because here addition is commutative, but if it's not commutative, so you have to keep the order. Yeah, this is the reason why we want to generalize something to be as abstract as possible so that we can apply to more new object. Now, provided it shares the same property as what we already knew before, so that we can apply our experience, our techniques, our computation that we had before to the new object, to the new concept. Yeah, this is nice. This is the purpose of generalization. Good. So this is the reason why we have to learn group. It's not for fun. This is for generalization. And as I said to you, this generalization is important in the fact that it allows you to use the old techniques, your old experience to show the new object, to work with new object. Okay, now we return to the slide.
Teacher, may I have a question?
Yeah, of course, you can ask.
We have already known the definition of binary operation, but I wonder why there is no such definition for an operation with three or more entries. And are there any concepts in algebraic structure that are based on these operations, like groups are created from the definition of binary operation?
We call binary operation because there are only here you have bi means that two operations together. Yeah. If you want to see three binary operations, no problem. You just multiply with g here. You can extend to any binary operations here. Bi means that the Cartesian product of two. Three binary, for example, Cartesian product of three is no problem. But the problem is what for? What you need that for? And when you find some application, you can define it, right? Here we find application for the old concept and extend to the new concept later for matrix, for example, we will learn later. Understand what I mean? You can extend to any if you like, but you should ask question what for. As I ask question here, why do we have to learn group? You know? Otherwise, nonsense. Good. Every time you can extend to everything that you imagine, but after imagining that object, you have to ask question what for, or the redundant subject. You have to find motivation for that generalization. Good.
Yes, but teacher, I have a further one more question. That's up to now we have discussed on group infinite group, but the definition of group do not require the set Z is an infinite set. So as far as I know, there is some finite group called as
Finite group. No?
finite group called a symmetric group. So what is so special about a symmetric group that can be used to describe the movement, describe the translation in space and in some critical chemicals critical.
It has so many applications which go beyond this lecture. For example, the theory of finite group can be applied to the code theory, theory for coding. But it's too much time to explain to you. Yeah, you need some background to understand what we are talking about. What?
Yes.
Yeah, there are many applications of finite group or finite field. So don't worry, you will find plenty of application. Even in the theory, in the field of coding theory, the finite group, finite field is fundamental subject for coding theory. Good. Here is the cancellation law. Um, in a group. So what I tell you in the whiteboard is the special case of this here, right? So in this, if you have a group, you can cancel in this way. So for example, A star C equal B star C, then you can cancel C to obtain A equal B. This is as what I cancel AX equal B. I cancel A by multiply by A prime. Here you just multiply by C prime, right? And actually, because the star may not be commutative, so you have to when you have equality, you have to keep the order in the same way so that you can cancel. Here you can cancel if they have the same order here, then you can take the star with C prime, right? But if C on the other hand side, then you cannot do that anymore because the star may not be commutative, right? So this cancellation law means that you can cancel C. So from A star C equal B star C, you obtain, it follows that A equal B. And from C star A equal C star B, you obtain A equal B. Good. And up to now, we have only structure, algebraic structure. On this means on G, we have only one operation. But now we can have more operation. For example, you see on the set of real numbers, you have addition, but you also have multiplication. Therefore, sometimes we have to consider two binary operations on the same set. And this leads to this concept rings. So the rings, we consider here a triple non-empty set V and then two operations, binary operation, plus or multiplication. And Well, here I repeat that V is not empty, and addition and multiplication here are binary operation on this V. Then we have V, this triple V plus multiplication is going to ring if and only if these properties are satisfied. So this V and plus is commutative group. This means that plus is commutative, associative, and there is a non-element. So not neutral element for addition is called non-element, you know, and then for every A here, there is minus A, you know, so that A plus minus A is none. Then the next property is the operation multiplication here is associative. And the next property is, you remember this property? The name is distributive property. You know, when you multiply A plus B with C, then you can multiply out as what we did in high school. But remember, the multiplication here may not be commute, you know, may not be commutative. So therefore, you have to write the property in different order. Of course, if the operation multiplication here is commutative, then you need only one order, because you change order, then it is the same. But here is the multiplication may not be commutative, so we have to write in both order, you know. And the last thing is V has identity element. This means neutral element related to the multiplication. Yeah, so related to this multiplication, we denote it by 1V as usual, and we call this 1V is multiplication identity or multiplicative identity. Good. So we can say multiplicative. You can use adjective or this noun. It's okay. It's no problem. An example. So actually, as I said before, in the definition of ring, we do not require that the multiplication is commutative. But if you are lucky, sometimes we meet the operation, we have the fact that the operation multiplication here is commutative, then we give more name to the ring. Yeah? So here the name is, of course, if in addition the multiplicative operation is commutative, then the ring is called simply commutative ring. Good. And then here is an example. Actually, we already knew this now. We knew that R with this addition, with this multiplication. Look again, you already knew R with addition is a billion. So commutative group, right? Here, the first thing is true. Operation multiplication is associative, and not only associative, but it's also commutative. And of course, we have this property of distributive property, clearly. That is what we already did many times in high school, in secondary school, blah, blah, right? We already knew the property hold true in the set of the numbers are. And of course, the identity element is 1, clearly. Therefore, you obtain this R plus multiplication is commutative ring. Later on, you will learn some more ring which is not commutative, you know. For example, for the ring of matrices, you know, then you do not have property of commutative for multiplication, as what we already saw with the composition. Sometimes the operation is not commutative, but still we still survive somehow, right? Again, Z plus and multiplication is also commutative ring. It's clear. And what is more? So later on, we will discuss the difference between this ring R plus multiplication and this Z plus and multiplication. Later on, you can think of, you can think about the differences between these two rings. Also, both of them are rings, are commutative rings, so this is nice enough, but is has some different feature. Yes, later on we will discuss this. But now let's go to the notion of trivial rings. Yeah, so this is a ring. V addition and multiplication is called trivial if and only if V contain only one element. So in that case, so because you have to contain both none and identity. So the none is neutral element for addition and the identity is neutral element for multiplication. So in case that it contains only one element, it means that these two elements are the same. So one V should be non V. Yeah? So because it contains only one element, in this case you see that nun multiply nun is again nun. So it plays a role as identity also, not only as non-element but also as identity. So this non-element also identity. Okay, this is trivial because we contain only one element, and in this case we write simply v is nun v, non v. Okay, then we will have some property here. So this is remind you something about what you learned long time ago, right? So this is still true now in the ring. So you have a ring V addition and multiplication. We denoted by none. 0 V is non-element. 1 V is multiplication identity. Then we have this A multiply none is none, and none multiply A is the same, is none. And V is non-trivial if and only if one V is not non-V. It clearly, because when they are the same, then it's only one element, because A multiply 1 is A multiply 0 is 0, for only. Therefore, if I want to have non-trivial things, then it's equivalent to the fact that these are two things, two neutral elements relative to multiplication and relative to addition should be different. And the last thing tell you that you have the distributive property for multiplication and addition, but it is also true for subtraction, where we define subtraction by b minus c simply equal b plus minus c, where minus c is negative of c. Negative of c means that the element such that when you plus with c you obtain 0, you obtain none. This is definition of subtraction. Then you have the distributive property for subtraction as well. Okay, let me prove at least one of them. So I proved the first one, and I think the other proof is so it's convenient for you. When I prove the first one, you will see it's a little bit strange and interesting. So let me return to the whiteboard and go to the whiteboard, and you see here are clear, and you have okay. What I want to start here was I start with a ring, which is a ring, right? And why I want to prove that so A and if element of V and nun V is non-element, no? So I read none, no? Non-element. This means neutral element related to the addition, no? So let me prove A multiply non V equal to none V. Then the same you can prove none V multiply A is also none. But let me write this way, because none V is neutral element. So this related to this addition. So you can write non v plus non v is non v. Yeah? So 0 plus 0 is clearly 0 because 0 is non-element, the neutral element corresponding to this addition. And now what I want to use property of distribution, distributive property. Okay, now look at the first and the last. Okay, I rewrite here so that you will see it's easier, right? Also it's 0, but you should write a little bit bigger than the usual 0 because this is neutral element of it can be any neutral element of this v, related to this addition. Okay, now you have a group because v with addition is group, so you have cancellation law. So I write one more thing here, non v, because non v plus this is this. Yeah, non v doesn't change anything with addition. Okay, now cancellation law means that you can cancel. Yeah, so whenever you have A star C the same as B star C in the group, it follows that A equal B. Now you can cancel. This is cancellation law, right? Cancellation law that you will learn previously. So therefore immediately you obtain non V equal A multiply non V. So similarly you can multiply non V with A, you obtain non V. So you obtain what you want to see, QED. QED means that the proof finished. Yeah. Okay, this is for you to see. You can do very formally, computation very formally, but actually this is exactly as what we were doing in high school. Now, but with a new object. The only thing that we need here is this new object satisfies the law of group, right? And everything goes smoothly. Good. This is proof of the first property. Do you know this word QED? This is Latin, cause erat demonstratum. This means that the thing is proved. You can search in Google if you like. This is a Latin word. It means that the proof is finished. Proof is done. Okay, so I return to slide again.
Teacher,
Yes.
does the trivial ring must have only one element? Is non V?
Yeah, non V and one V is the same. It's equal.
So
Yeah.
non V is the null element of the ring.
Yeah, and also the identity of the ring. In this case, the two neutral elements are the same. Yeah.
Yeah. Okay. Okay.
Is it clear? Good.
Yes.
It's very special because this is trivial. Yeah. Okay, now we return to the slide and go to the next point. Now we consider the notion of field. This is for definition. You have very simple definition, but as it is very simple, so it's a little bit difficult to understand. So I will explain in detail. So by definition, this triple V with addition with multiplication is gonna fill. It is a commutative non-trivial ring such that if A in V and A is not none, where we know that none V is a neutral element related to the addition, then it has an inverse A to the minus 1. This means that so the multiplicative inverse, so this means that A multiply A to the minus 1 is 1V. So we say shortly, a field is a commutative non-trivial ring such that if A in V and A is not non-V, then A has an inverse. But let's write down a little bit in more detail, no? So this triple V addition and multiplication is a field, even only, of course, by definition of a field of a ring. So look at this is commutative, non-trivial thing. Yeah, so V plus should be commutative group. The operation multiplication here is not only associative but also commutative. And we have the property, distributive property. This case we have to write only one order because the multiplication here is already commutative. You know, if you change the order, then you obtain the same. You know? And V has identity element relative to multiplication because now you have non-trivial things. So 1V should not be 0V because here you have the property above. So 1V is not OV, not non-V. And now the last thing is corresponding to the last statement here. Means that if A in V, A is not none, then there exists A to the minus 1. A to the minus 1, that means that inverse of A, you know? Means that A to the minus 1 multiply A is 1V. So this is called inverse of A. So A to the minus 1. Good. And we can look back. You can look back at this, as I already asked you before, what do you think about the difference between these two rings, although both of them are commutative rings, but this R plus and multiplication here actually so few, because it's of course the commutative rings, non-trivial rings, right? And every non-zero terms, non-zero element has inverse. So if A in R and A is not zero, then A to the minus 1 simply 1 over A, right? Then it has inverse. But that property doesn't hold in this that Z addition and multiplication. For example, if you take number 2 in Z, but 2 inverse of 2 is 1 over 2 is not in Z. Yeah, so this is not a ring, not a field anymore. Although it is a commutative ring. So this is again you have a field. A field is very convenient to compute in. For example, you can show an equation not only for addition but also for multiplication. Actually, you have to require only the fact that A is not none, that you can show equation AX equal B. When A is not zero, then you can take the inverse of A to eliminate A, right? And actually, what you have here also nice. I give you here two examples. I have to mute all, no? And if you have any question, you just turn the microphone on and ask me, no? Good. So you see R plus and multiplication here, of course, as I said before, this is the field, not only a commutative, non-trivial ring, but in this ring you have every non-zero element always has an inverse, so multiplicative inverse. Yeah, the same for Q with addition and multiplication. It's also a field because when x in Q and x is not zero, then you have x to the minus 1 exists. This means 1 over x. Yeah, it's also in Q. Of course, I write notations convention. Yeah, so for multiplication, we just write AD without any point. Of course, if you write points, okay, it's more comprehensive. But if you do not write multiplication point here, it's okay, it's no problem. Yeah. Okay, now I'm going to tell you about complex number. Before I am doing that, I just ask you a question. You already knew about complex number and the set of all complex numbers denoted by C, no? So here is a C, no? But do you believe that, okay, let me share this whiteboard and write question in the whiteboard so that it's easy to see, you know? The question is, do you believe that there is a number I such that I square is equal to minus 1? Now, the question is, do you believe that there exists I such that I square equal minus 1? Answer me. Is, is there anyone who believes this? Or is there anyone who doesn't believe that? Tell me. All of you believe that? Or none of you believe?
Yeah, we do believe it.
Hmm? No one believes that, or someone?
I believe that I squared equals minus 1.
Oh, you believe that, no? It's random because how can you? The question is, how can you? How can you describe I? Or how can you imagine?
I think it's theoretical. It's not realistic.
I
This
mean,
is not. This is
you
not real.
can like you can draw the OXY thingy. How do you call it?
So therefore, my purpose in the next section is my purpose is to convince you that there is I, and I will show you how to construct such an I such that if you already believe so, maybe you can leave the class. You can stop listening to me because this is my purpose for the next point is to convince you that there exists I such that I square equal minus 1. Yeah, this is my purpose because I should tell you that in when I will told for the first time when the teacher told me that there is this certain I so that I square equal minus 1. Actually, I didn't believe. Yeah. Why? How can you describe me? How can you say that this is nonsense? Good. Because I cannot imagine how can you multiply something to obtain minus 1, you know, because this is unreal. So this is some kind of divider means. But I will tell you, I will show you. Actually, there exists such an I such that I square is equal minus 1. And now I will construct such an I. So if you already believe so, no need to listen to me, right? No problem, but I will tell you. Okay, okay, this is the field of complex number. Good. This point is firstly I construct a set, and on that set I have binary operation. You know? So the two binary operations which are addition and multiplication. Okay, our set is very simple. We have this R square. R square means that R times R. So the Cartesian product of R and R. We already knew this R square from high school, you know. And on this set, we consider that additive and multiplicative operation. So they are binary operation defined this way. So we have addition is simply a map mappings going from R square times R square to R square. So it defines this way. So you take a couple in this Cartesian product. So the couple of element AB and CD, and it's mapped to the sum AB plus CD defined this way. So it's very simple. Use it as a corresponding component. No? So A plus C and B plus D. This is very natural definition for the addition. Yeah? But for the multiplication, it's a little bit ridiculous. So you have A, B, C, D, and so you have to define the multiplication of these two elements. Yeah? So the AB multiply CD, and we define as follow. So we take A multiply C and then minus B multiply D, and this plays a role as the first component, and the second component is AD plus BC. Actually, you see, these assignments are well defined. So you have mappings. Therefore, you have binary operation. And now let me check first that this R square and these are two binary operation, addition and multiplication, actually form a field. So to do that, you have to check this R square. Okay, our purpose, the first purpose is to check that R square with addition with multiplication defined that way is a field. Actually, you have to check this is a commutative. It's clearly because the addition here commutative, because the addition of the real number is already commutative now, and non-trivial thing ring. Yeah. Actually, the multiplication is also commutative, so you have commutative ring. Yeah. Non-trivial thing, it has infinitely many elements, so it's not trivial, because trivial means that it's only one element. No. Here it has infinitely many elements. R square has infinitely many elements, so it's non-trivial. And of course, with the non-element, it's easy to check 0, 0. You can check it here. AB plus 0, 0. Again, you obtain AB. And identity is 1, 0. Different from 0, 0. In non-trivial, you always has this property. So we can check AB multiply 1, 0 is AB, right? Okay, this is routine work to check. This is a commutative non-trivial ring with non-element 0, 0 and identity elements 1, 0. It's not difficult. It's long. Of course, for example, when you check the property of associative, a little bit long, right? But it's not difficult. It's very long, sometimes long, but not difficult. So I don't want to check. You can check. It's just show. But I don't want to take here. I want to take the last property. So you have here, this here. To check your field, you have to check this everything here. But it's easy to check commutative group with addition and the associative. Also, it's long, but it's easy to check. And this law is also a little bit long to check. This this distributive law between addition and multiplication. And it's long, but it's easy. Yeah. I don't check, but I will take the last one. If A and B is not none, then there exists inverse of A. Yeah? So A has an inverse. In this case, it has a form AB is not 0, 0. Then actually you can choose the CD in this way, so that when you multiply AB with CD, you obtain 1, 0. But I will tell you how to obtain the CD. Yeah? Because we have the whiteboard here. So I will compute on the whiteboard in easy way to show you how to obtain this inverse of AB. look at this. Okay, again I will do the last property of a field now. I will do this. So actually what we have here, I write again this definition of multiplication now. By definition, this is AC minus BD and AD plus BC. This is the definition of our multiplication now. And now we take AB, which is non-zero, zero. So this is a non-element now. And we want to find CD such that AB multiplied CD is 1, 0. No? So what does it mean? AB is not 0, 0. It's equivalent to at least one of A or B is not 0. It's equivalent to the fact that A square plus B square is not 0 because A, B are real numbers, right? I remind you that when you have equality, AB equal EF, for example, in the Cartesian product, this means that you have corresponding components should be the same. This means when it's different, then you need at least one of these is not true. No? So you have or here. No? And now we find CD in this R square, right? Such that AB multiplies CD equal 1, 0. And you multiply this here, you obtain AB multiplies CD is AC minus BD. So you obtain AC minus BD and AD plus BC, right? Equal to 1, 0. And again, I already remind you what's the equality in Cartesian product. This means that AC minus BD equal 1. At the same time, AD plus BC equal 0. So we want, so now AB are given. So this is given. Given AB, which is not 0, 0. This means is satisfies this. Given AB satisfies this condition, we have to find CD, right? Okay, I want to eliminate minus BD here, then I multiply A with the first, and here AD, so it's B here, right? Then adds together, so you obtain A square when you multiply with A, and ABD, and here you obtain BAD, it's disappear. The only thing is B square here. And on the other hand side, you have A here because A multiply 1 is A. So you obtain C equal A over A square plus B square. Now you replace this here to obtain D, right? Actually, you obtain this minus because you have to change here, so minus BC over A. And after you divide by A, you obtain minus B over A square plus B square. So all together you obtain CD. So CD equal A over A square plus B square, and then minus B over A square plus B square. And this is the inverse of AB, because multiply with AB you obtain 1, 0. No, this is actually inverse of AB, as I write in the slide. Yep. So therefore we had the fact that this R plus with this R square with addition and multiplication clearly is a field, right? So we return to slide now. Return to slide. Good. Where's my slide? Let me check. Good. So you obtain this r square plus and multiplication actually is now is a field, and therefore what I want to tell you, as I promised before, is I want to convince you that there is a number I, so that I square equal minus 1. I want to look for number I in this set I square, but actually you see something ridiculous here. I square, element of I square has two components, A and B, but minus 1 is only one element. How can we coincide? How can we identify this element of two components and the other elements only one element? It seems impossible, but impossible that means that I am possible. So I try to do this way. So let's present present r square in this plane as x or y, as in the seventh class. You already has this coordinates plane, you know? So it's like y. So every element of r square can be represented as a point AB. Yeah? And pay attention to the horizontal axis. So OX, so horizontal axis, you have here every point in this OX in this horizontal axis has a form A0. The second component is always 0 because it is in the horizontal axis now. All of the second component of the point in this OX is 0. So we have the form A0. Now let's do the computation here. Of course, the computation we have to do in this way, you know? By definition, on this set R square is to binary operation here. But when B0, C0, then the sum is simply A plus C, and the second component is 0. Here also, when B0, D0, then the multiplication of A0 with C0, the AC minus 0, and then the second here also 0. So good. Actually, we compute A0 plus C0 is simply A plus C. Is the second component is always 0. A0 multiplied C0 is AC and 0. So second component, whatever, is always 0. And actually, the operations that we are doing here, we operated here, the same as addition in R. A, C, the A plus C. And the second component kept unchanged, it's always 0. And here A0, C0, simply AC. So the multiplication in R. So this means that we can identify every point in this axis, in this horizontal axis, with a number, with a real number. So I do the following identification. A0 with A. What does it mean, this action? This action just means that we take the real axis, you know, the axis of the real number R from outside, and then we put it here. Put it coincide with this horizontal axis, and we consider this is the axis of real numbers R. This means we identify every point here with the real number, and it's reasonable because it exists as a real axis, you know? So the axis of real numbers. What we are doing is to identify is A0 with A. And now we take number I as follow 0, 1. So number I should be somewhere here, right? And compute I square. So I square means that I multiply I. So 0, 1 multiply 0, 1. So using this formula here, 0, 1, 0, 1. So we obtain 0 minus 1. And second is 0. Oh, we obtain this is minus 1, 0. But using this identification that we had here, you obtain this identify with -1. So you see I square identify with -1. Something stranger here because I use a trick, right? So I use identification as trick. So every point in this horizontal axis I identify with the number in R, and this identification allow because every time I am doing computation on this axis, it's the same as I am doing the computation in R because the second component is always 0, you know? And we are doing with only the first component, and the addition and the multiplication are operated exactly in the same way as in R. So therefore this identification is allowed, right? And I worked in this. So now you see the number I, actually the I has this form, and after take raised to the power 2, so take square, and after a reasonable identification you obtain -1. It's not only that for fun, it's for another representation I want to use here. So now you have AB in R square can be written as, so A0 multiply 10. This is the product, the rule for product for the multiplication that we had before. And B0 multiply 0, 1. So you have A0 is identified with A. So we obtain A. 1, 0 is identified with 1. So A multiply once again A. And here B, and this 0, 1 is I. Yeah, this is number I here. And you obtain A plus BI, and you obtain the set. Actually, you can identify this set with R square, but I like to write this set in a new name, and the name is C, and denote the C by the set of all the number of the form A plus BI, where AB is real numbers and I is numbers such that I square equal -1. So actually it's exactly this number 0, 1, but after identification, this identification leads to the fact that I square equal -1. A number I is called imaginary unit. Yeah? And we can see the set of complex number. Good. And now you see that as proved above, we already knew that the C with the addition with the multiplication is the field, and we call it the field of complex numbers. And actually, I have to tell you again how to compute this addition and multiplication on this set, because if we are doing in that way in this definition, then it's too complicated, yeah, and so it should not be done in this way. This is so ridiculous. So I will tell you how to compute that. Okay, let's start by the addition. Yeah. So by definition, if you do additions, and you have to turn it to the couple here. So A plus BI is a couple AB, C plus DI is couple CD, and then you add by regulations that we had before. So A plus CB plus D. But this already identified with A plus C plus B plus DI. This is our identification for the set C. Actually, now we can forget the ugly thing in between here. Just forget this part from here until here. The look at the beginning and the end. You see that this is very simple. You just do as what you did in the set of real numbers are. So the take A plus C and B plus D, put I as common factor, and you obtain B plus DI. So the difficult thing you can forget, yeah. And it's best. It's very interesting that you can do the same thing here with multiplication. Of course, if you want to compute multiplication by definition, then you have to change AB to couple AB, and then C plus DI here, couple CD, and then use the definition AC minus BD, AD plus BC, and at the end you identification that we had, you obtain this AC minus BD plus AD plus BC. I. But actually, now I tell you, you can forget this difficult definition here, ridiculous definition here. You should look at the beginning and take a direct computation here. Use the computation, use the compute AC plus A B I D I, it become B D I square because it contains I and I here. And then A D I B C I and put I as common factor. So you should do as what you were doing with the set of the numbers, right? And take into account that taking into account that I square is equal minus 1, so you obtain this is minus BD, and this is AD plus BC, and I is common factor. So it's the same result as above. What does it mean? This means that you can forget the ridiculous definition. What you have to remember is, so the calculation is done by usual ways as in the set of the numbers are, with the tension that I square equal minus 1 is you should compute directly. Okay, now you know how to compute this. Now you don't have to remember definition of the multiplication and addition anymore. You should do exactly as what you did in the set of great numbers are. Everything is the same. The only thing that you have to pay attention is whenever you meet I square, then is you can replace I square by minus 1, right? And everything is done. Okay, this is good. This is the way now it's easy for you. Now it's maybe you already knew in high school. What is going on next is plays a role as review, so that you can do computation easily. So here I remind the name. This number I is called imaginary unit. And the representation of z as z equal a plus ib is called canonical form or algebraic form of z, of a complex number z. In this form, you have a plus bi, then a has a name, and the name of a is the real part of z. So if you have z equal a plus bi, then this number a, the real number, is called real part of a of z, and the number b here, the coefficient of I here, is called the imaginary part of g, and denoted by a equal re z and b equal in z. Right? Good. Actually, z equal re z plus I multiply in z. Yeah. And as usual, when we have a new object, we have to compare two elements, and the comparison here very simple. Two complex number in algebraic form or in canonical form are equal if and only if they have the same real part and the same imaginary part. Yeah? That is to say that z1 equal z2 if and only if re z1 equal re z2 and in z1 equal in z2. So a1 equal a2, b1 equal b2. It's clear because it's the same as equality in Cartesian product. So you can look at a plus b1i as couple a1 b1, and then z2 here as couple a2 b2. They are the same if the corresponding components are the same. So a1 equal b1, a1 equal a2, and b1 equal b2. Good. This is simple. And what I want to tell you more is subtraction and division in canonical forms can be done in the same way as in R. There's no need to tell you because you know how to do this now. But let's pay attention to division. Okay, subtraction is done in the same way as in R, so you just put I as common factor and everything goes smoothly, right? For division, so you have to divide, then on the denominator it should not be 0. So by definition, the division means that you multiply with the inverse, and you have the formula for the inverse. But we never done in that way. It's complicated to remember inverse. Now we do the following way. We had the practical rule. So we compute, if you want to compute this fraction, then actually you should eliminate this I by multiplying both denominator and numerator with this A2 minus B2I. Then on the on the denominator you have A2 square plus B2 square. There is no I more, right? Because I square is minus 1. And then on the numerator you should obtain something else, then you just simplify. This is you already learned in high school. I don't want to repeat too much that you already learned, because we want to go to some more important concepts. Now you have more chance when you are doing exercises. Okay, now let me tell you again how to represent complex numbers on a plane. This we call complex plane x or y. The plane that we used before when we want to show you what the imaginary axis or imaginary unit is. So the complex plane is simply the coordinate plane x or y. This is coincide with r square as we used before. You see, here you have two ways to represent complex numbers on this plane x or y. I call it two interpretation. For complex numbers, the first way is we can consider complex number as a point. So mxy, so the number z can be considered as xy, the point with the coordinates xy. It belongs to xyz, and this x simply identified with x0 as what we did before. And this is the real part. Therefore, this axis here, the horizontal axis, is called the real axis. It's exactly the axis of real numbers. You see that we bring the axis of real numbers outside, we put it here. So this is R. On a point in this horizontal axis, simply a numbers, real numbers. So we call this real axis, and here the vertical axis. So contain on the point of the form OY, you can write this I multiply Y. You can write 0, 1 multiply Y. So obtain IY, where Y is the imaginary part. So therefore this vertical axis is called imaginary axis, right? Good. And we already saw this representation before when we performed the way to find this number I, so that I squared equal minus 1. And the second way, this is the first way, we consider complex numbers as points. And second way is to consider complex numbers as vectors. So here OM, I make it a little bit bigger, right? So here the vector x plus iy can be considered as a vector from O to M. Now this is O, the origin, and this is the endpoint M. So the coordinates of this vector is xy. You can write as coordinates, or you can write simply equal xy. Then what you have here is the sum of two complex number. Now you can see is simply the sum of two vectors. Then you have a rule, and the rule is called parallelogram. which is the diagram of this parallelogram. So therefore, the rule is called parallelogram rule. No, so you have this u complex number u plus complex number v, simply the sum of two vector u and v, and this is the sum, right? Good. Also in this representation of complex numbers as vectors, you have some other notation like conjugate. This is u, the complex number u, and the conjugate u bar is simply defined as follow. I have here. Um, so for u equal x plus iy, so I write here c, but now I use another letter. So u as a letter, you can do any letter you like. You know? So the complex conjugate of u is simply u bar, which is equal to x minus iy here. So the symmetry of u across this horizontal axis. No, so u bar is x minus iy, and I list here some of the property. You know, so I make it smaller. Good. So you have these properties that you learn in high school. And I don't want to pay too much attention here because you already learned in high school. I just review is here so that you can I can remind you something that you learned in high school. Then you can apply to work with exercises. You know, you have more chance to practice when you working with exercises. You know, so here the properties that I list. The property of complex conjugate. Yeah. So the conjugate of the sum is the sum of conjugate. Conjugate of a product is product of conjugate. Conjugate of division is a division of conjugate. And for z and c, you have the fact that z is a real numbers if and only if the conjugate of g equals z. Okay, clear? Okay, you can remember all of what you were doing at high school, right? And I'm going to the next point. So we have about 5 minutes more. So I introduce. Okay, I remind you the modulus you already learned in high school. No, what is new for you is some other form. But before coming to this new form, I have to remind you the old form that you learned in high school, so that I can systemize your knowledge. Now, it's better for you when I review a little bit what you already learned, you know, in high school. Actually, you have the modulus of this complex number denoted by this absolute value, or now you read as modulus. Now, so if z is a real number, it is coinciding with absolute value. But now z here is complex number, so you have to read modulus of z, simply square root of x squared plus y squared. So this, the sum of the square of real part and imaginary part. You know? Actually, this is the length of OM. You know? When you use a vector OM to represent the complex Z, then this modulus is the length of OM. Actually, this is square root of x squared plus y squared. If you look at this OM here, this is OM, and this is x, this is y, and the length of OM is exactly the square root of x squared plus y squared. So the modulus of z exactly is the length of the vector that represents z in the complex plane, right? Good. And now again, I remind you some property that you already knew in high school. Can you see this? So the modulus of a product is product modulus, and you have the parallelogram equality. So can you recognize this equality? And you know the reason why we call it parallelogram equality. Okay, I draw a picture here, you know. So let's go to the whiteboard. You know, I share the whiteboard again. Where's my whiteboard? Zero moment. So you have okay. I had here the whiteboard. Where's my whiteboard? Okay, I found it. Okay, now let's take Z1, Z2 in the set of complex numbers. So you have this F as the modulus of Z1 plus Z2 plus modulus of Z1 minus Z2 square. So square plus square equal to multiply modulus of Z1 square plus modulus of Z2 square. This is called parallelogram equality because of the following reason. You have now we use the vector to represent so this is O, no? So this is Z1 and the other is for Z2 and then actually using the parallelogram rule, you have this is Z1 plus Z2. So Z1 plus Z2. And this part here is Z1 minus Z2. So this equality, this means that you have the sum of the square of two diagram. The sum of square of two diagram is the sum of the square of two vectors here. No? You have here again Z2, here you have again Z1, right? So you have, so this is called parallelogram because this is actually parallelogram that you learn in geometry. You know? So the sum of the square of two diagrams is the same as the sum of square of four sizes. You know? The length of four sizes. Yeah, you have Z1 square plus Z2 square, and here is Z1, Z2, so multiply by 2 is the length of the square of all sizes here, right? It's the same as the sum of square of two main diagonal diagram. Now, good. We already the time is already up, so we have to finish here. I'm also tired. I have 6 hours today, so this is too much now. Okay, so time is up, and I have to finish it here. Good, and I will upload, right? I will upload this unit slide. Yes or
Yes.
no?
Yes.
Of
Yes.
course,
Yes.
please
Yes.
upload it.
Upload slide because actually principle in principle, the slides are almost the same as textbook, but I just write something shorter and clearer, huh? So you can read easier. Okay, time is up. So I stop here and wish you all the best. Yeah. So see you next time.
Goodbye, teacher.
Stay safe.
Goodbye.
And
Goodbye, teacher.
Okay, my teachers.
Goodbye, teacher.